Okay, thanks everyone for joining. So today we have Ashwinee and Xinyu from Princeton telling us about improving the privacy utility trade-off in differential privacy with public data.
Great, thanks Thomas. So I'm Ashwinee.
I'm Xinyu. So I'm a PhD student from Princeton University, and I will just let Ashwinee to start.
Yeah, so we're interested in the privacy utility trade-off in differential privacy, specifically differentially private machine learning. The reason that we care so much about privacy for machine learning models is that these models are very powerful and they're trained with private information from individuals like you and me. So whether that looks like large language models that can memorize your phone number and then spit it out with a specific prompt, or generative models that can memorize a specific image of you, it's risky for these models to be trained on so much private information without really understanding how they might leak that private information. Differential privacy is one very useful way of quantifying the risks of privacy. When we have some specific properties on our data sets, we can actually provide a provable guarantee that the model that is trained on that data set does not leak too much information about its training data. And we can do this by using differentially private stochastic gradient descent, or DP-SGD, as our training algorithm instead of the regular SGD that you're used to. DP-SGD has two key variations from SGD. First, we limit the sensitivity of any individual data point. That is to say, we limit the influence that any data point can have on our final trained model by clipping each gradient that we see to a predetermined threshold. This introduces bias. And we also add noise, in this case, Gaussian noise, to each gradient update, which introduces variance. Now, this introduced bias and variance can and will have an impact on our model's utility. In fact, we expect that DP-SGD should incur some utility drop because we don't expect to get privacy for free. And prior work has observed this extensively. Even on a benchmark as simple as CFAR 10, we'll see as much as 30% degradation from the non-private baseline when using a reasonable privacy guarantee like epsilon between 1 and 2. In our talk, we want to bridge this utility gap between the private and non-private models. And of course, privacy doesn't come for free. So the specific tool that we're going to use to bridge this utility gap is public data. We want to leverage public data to improve the privacy utility trade-off in this kind of privacy-preserving machine learning with DP-SGD. So what exactly is public data? Well, we can think about pre-trained models that are publicly available on sites like Hugging Face that were pre-trained on large data sets. And we can also think about task-specific data. For example, some users might opt into sharing their information on iPhones, even with Apple's ATT. And this opt-in data might be a very small sample, but we still might want to take advantage of it when training a model for a specific task. So in this talk, we're going to be talking about two approaches for when you have a lot of private data, a lot of public data, or not so much public data. When there's a lot of public data available, and we can in fact get a model that's pre-trained on that public data, we're going to propose a new linear scaling rule for differentially private fine-tuning. And when limited public data is available, we're going to propose DOPE-SGD to efficiently use this limited public data in privacy-preserving machine learning. At a very high level, we want to give a quick overview of these results. So when we can have a pre-trained model that's publicly available on this large data set, the linear scaling rule allows us to provide competitive results on all values of the privacy budget epsilon that we consider on the competitive ImageNet benchmark, where here the SOTA was referenced to Meta et al. From 2023. And DOPE-SGD, when there's a limited amount of public data available, can provide a substantial improvement on DP-SGD with a warm start by efficiently making use of this public data. So first, I'm going to talk about our new linear scaling rule when a model is available that's pre-trained on a lot of public data. And the key takeaway is that our linear scaling rule accounts for the privacy cost of hyperparameter search and takes us into a new regime of hyperparameters for private fine-tuning that unlocks better performance across a wide range of tasks from computer vision to natural language processing, including domain generalization tasks, where we're able to provide substantial improvement over the prior state of the art, even when the pre-trained models that we're working with have similar non-private accuracy. So there are a few key questions that I want to answer in this portion of the talk. How expensive is hyperparameter search in terms of privacy? Can we improve this with a search method that takes into account the privacy utility trade-off? How can we optimally train these pre-trained models with private fine-tuning? And what ultimately is the gap between private and non-private fine-tuning? So to understand the privacy cost of hyperparameter search, let's start off from the basics. In this talk, we're going to be looking at two ways to do fine-tuning. Given a pre-trained model, we can either update all the layers, or we can freeze the feature extractor part of the model and just create a new classifier. In either case, the performance of the model is very dependent on the learning rate and the momentum. As we all know, deep learning needs a lot of hyperparameter search. And DP-SGD also needs hyperparameter search. The clipping and noise that we introduce are going to shift the bias variance trade-off from non-private training. And we want to be able to optimize the signal-to-noise ratio, or SNR, of our gradient updates. In particular, we know that the noise will depend on two factors: the number of iterations, the number of epochs, and the learning rate. So what we find is that the lighter squares, where lighter is better, tend to depend a lot on the number of epochs and the learning rate. Our performance is very heavily dependent on these hyperparameters. And this is a plot for epsilon equals 0.01, which is a very strict value of the privacy budget. But as we increase the privacy budget, we can see that the lighter squares move. That is to say, the optimal hyperparameters depend on the privacy budget. As we increase the privacy budget, the best values of the learning rate and the number of epochs trend towards large learning rates and taking a lot of iterations. So the best hyperparameters for DP fine-tuning depend on a lot of factors: the dataset, the model, and the size of the privacy budget. With all of these hyperparameters, we need to take into account how much is this going to cost us in terms of privacy. This is a figure from a recent survey paper, coincidentally also out of Google. So if we just take the simple approach of treating each hyperparameter tuning run with adaptive composition, we can see that the additional privacy cost of doing hyperparameter search is going to quickly increase our privacy budget. And this is going to have pretty negative ramifications on our privacy utility trade-off. We'll get into exact numbers a bit later, but it's easy to see that this kind of hyperparameter search is not free, and it's not even cheap. Now, there's obviously something better than just doing grid search with adaptive composition. And there are prior methods that scale much better than adaptive composition, which scales in the square root of the number of trials. And we're not going to get too much into a comparison with these methods because, as we'll show, they're actually compatible with our work. So the privacy cost of hyperparameter search is large because the optimal hyperparameters depend on a lot of things, which means that we need to retune them often. We can't really transfer them between private and non-private, between data sets, or even between values of the privacy budget. And although prior work typically does not include the cost of hyperparameter tuning when they report their privacy utility trade-offs, this is something that we want to do. We want to be able to incorporate the privacy utility trade-off into a search method. So let's start off from what we know intuitively about DP-SGD. As we add less noise and therefore have a less privacy budget, our signal-to-noise ratio of individual gradient updates will improve. This means that we can afford to take a larger learning rate, larger step size, and also have more iterations while preserving the same signal-to-noise ratio. So this gives us two key ideas right off the bat. First, we're going to reduce the dimensionality of hyperparameter search by folding the learning rate and the number of epochs into one parameter, the total step size, which is the individual step size times the number of steps. And we'll refer to this as R in our equations. And also, we know that as our noise gets smaller, we should be able to increase R, the total step size. Or in other words, as we increase our privacy budget, we should increase our total step size. So in order to account for the privacy cost of hyperparameter search with this linear scaling rule, we're going to do search with small privacy budgets and scale it up. Now I'm going to get into an example of how we can apply this for CFAR 10. So if we start off with a total privacy budget epsilon, we can split this up into 3 pieces. And we'll go into concrete examples of how we split this up as well. So we'll start off with a very small privacy budget, something like 0.01. And we'll do a few trials here to estimate the best value of the total step size at this very small privacy budget. And we're going to do the same thing with a slightly larger privacy budget, in this case 0.05. And now we have 2 values of the total step size that we've estimated at 2 different points on the privacy utility trade-off. So we're going to use these 2 points to just do simple linear interpolation. And the reason that we're doing this very simple linear approximation is because we really don't want to get too complicated with how we estimate this total step size. We'll then use our new linear scaling coefficients to estimate the best value of the total step size at the leftover privacy budget, in this case 0.9, and we'll train a model with that privacy budget to output a model that is epsilon private while including the privacy cost of hyperparameter tuning in producing that model. So I'll pause here for a second and note that, of course, these values, epsilon 0, epsilon 1, epsilon f, and the number of trials have to be specified. But I'll show that generally we use very similar values for these splitting epsilon and how many trials we want to do. And it is typically a very small number of trials. And of course, the linear scaling rule then can be stated quite succinctly. We want to use a small amount of our privacy budget to search for the best value of the total step size. And then we're going to scale up that value of the total step size as our privacy budget increases. And this basically means that we're just increasing the learning rate and the number of epochs as our privacy budget increases. Now, as I mentioned, we're doing a very small number of trials at each privacy budget. That means that each individual trial has to have a lot of information. Otherwise, we risk just wasting our privacy budget. So we also want to be able to really optimize this fine-tuning from pre-trained models. And we're going to do this with a recipe that really optimizes our private fine-tuning. So just to set things up here, we're going to have a private data set that we extract features from, and we're going to initialize our model at 0, operating on these extracted features. We'll use the linear scaling rule to determine our step size and number of steps, and we'll use PLV accounting to figure out how much noise we're going to add at each iteration. This is just figuring out the hyperparameters and how we're going to initialize the model. At each iteration, we're going to compute the full batch gradient because the full batch optimizes the signal-to-noise ratio. We're going to clip that gradient to a unit clipping norm because, as we find, clipping any further actually introduces bias that degrades performance. And we're going to add noise to this to make it private. Now that our gradient is private, we can take a step with momentum in the direction of this private gradient. And the reason we use momentum is to accelerate convergence and reduce the overall number of iterations that we need to reach a good solution. Here, the learning rate is given by the linear scaling rule, and the number of iterations is also given by the linear scaling rule. The linear scaling rule will give us some value of the total step size, and we can just randomly decompose this into something that seems reasonable. And we'll show you some examples of how we can do that in our results. After the iteration is done, we're going to do something that looks a little weird. We're going to take one last step in the direction of the momentum buffer. And recall, this momentum buffer is private via post-processing. So we don't need to add noise to this final step. This step may seem pretty small. And for the optimal hyperparameters, it is pretty small. We don't really see improvement beyond maybe 1%. But if the linear scaling rule gives us some combination of hyperparameters that produce a model that is very underfit, that means that there's a lot of room for improvement. And taking this final non-noisy step is going to give us a lot of improvement for those underfit trials. This allows us to really maximize the value that we get out of each individual trial, even when we're doing random trials given to us by the linear scaling rule. And this is going to output our final trained private classifier. So we can summarize this optimal recipe with zero initialization, full batch gradient descent with momentum, unit clipping, and finally, a free step in the direction of the momentum buffer without adding noise. Now that we've come up with a way to incorporate the privacy cost of fine-tuning and a recipe that optimizes how to do fine-tuning, keeping in mind how to optimize the signal-to-noise ratio of each gradient update, we'd like to understand the gap between private and non-private fine-tuning. So our empirical analysis covers a range of tasks from computer vision, ImageNet, domain shift tasks, and natural language processing, including the GLUE benchmark. Across all of these tasks, our experiments include the cost of hyperparameter search. So first, let's just validate our linear scaling rule. What we find is that the linear scaling rule privately approximates grid search. Here, grid search is doing about 100 trials, and you may be able to get away with fewer trials for grid search, but the point is that grid search costs a lot more privacy than what is being depicted on the x-axis epsilon here. But the linear scaling rule includes the cost of hyperparameter search in all of these data points. So the linear scaling rule produces hyperparameter combinations that are almost as good as grid search, but is an order of magnitude as private. And again, you might be able to improve the cost of that grid search by using some other methods for doing that hyperparameter search, but you could also do those methods for hyperparameter search inside of the linear scaling rule, and therefore any improvements to the baseline here can also be applied to the linear scaling rule. So as I mentioned previously, the work by Papernon and Steinke can also be used in conjunction with the linear scaling rule. And linear scaling also beats prior work. This is meta et al. From 2023 on ImageNet. And here we're giving you some specific examples of what the total step size looks like. All the way down at a privacy budget of 0.05, the best values of the learning rate in netbox are 10 and 10, and that increases all the way up to 20 and 100 for an epsilon of 2 or larger. And across all of these values of the privacy budget that we can consider, we see that the results that we obtain with the linear scaling rule outperform prior work. In particular, this is because the hyperparameter combinations that we are obtaining from the linear scaling rule are so different from prior work, which is just doing a single step, really, of sin SGD. And as you can see, this linear scaling rule scales up to values of total step size that are very, very large. So now we're going to get into a few specific questions. So far we've been considering private fine-tuning from a public data set and then testing on another data set. And there's really not been any distribution shift between the public data that we use for pre-training, the private data that we use for fine-tuning, and the private data that we use for testing. And in these experiments, we're going to be using the linear probing variation of fine-tuning. So the first question that we'd like to ask is, can differential privacy help when there is a domain shift between the private fine-tuning training data set and the private fine-tuning test data set? So to answer this question, we're going to look initially at waterbirds, which is a well-known data set that contains a spurious correlation. And what we find is that although there is noticeable accuracy degradation from non-private training for the in-distribution class, the out-of-distribution class, which is negatively affected by the model overfitting to the spurious correlation in non-private training, performance on that actually improves. And this kind of makes sense intuitively because our privacy should be mitigating any overfitting that we're seeing from the private fine-tuning training data set to the test data set. We also see this kind of domain shift in our other data sets, but these data sets also answer the question of what happens when there's a domain shift between the public data that we use for pre-training and the private data that we use for fine-tuning. Here we're looking first at the functional map of worlds dataset, which is satellite imagery of buildings, the chameleon dataset, which are medical images, and domain net, which contains images that are sketched or painted or drawn or some other variation of how the images are depicted. Each of these datasets has a significant domain shift from our pre-training dataset, which is ImageNet. And again, we see that we are able to mitigate the big domain shift between private fine-tuning training and testing. And furthermore, the impacts of the domain shift from the pre-training dataset to private fine-tuning do not seem to be exacerbated at all by differential privacy. Finally, we want to see whether the models that we fine-tune with DP can perform well in the zero-shot setting. So here we take models that are privately trained, fine-tuned on CIFAR 10, and then we zero-shot evaluate them on STL CIFAR 10.1, which is another minute distribution shift, and the common corruptions versions of these data sets, which are CIFAR 10C and CIFAR 100C. And we find that even when we don't need to do any kind of training on the final downstream task, the DP fine-tuned model performs quite well. And this means that even when the dataset pipeline continues beyond the point at which the practitioner has implemented differential privacy, as long as the pre-trained feature extractor is sufficiently good, these DP fine-tuned models can perform quite well. The next setting that we're going to be getting into is specifically looking at linear scaling for the linear probing setting. And we want to answer three specific questions here. What kind of models work? And are different models good for different data sets? And how does the private, non-private utility gap depend on the model? So we evaluate both transformers and convolutional architectures here. The transformers are vision transformers and the convnet is convenext. And both of these work quite well with linear scaling, obtaining very competitive performance on CIFAR 10. And the best model overall, the BEIT v2 from Microsoft, performs the best on all of the datasets that we consider. So that means that the same model is the best on all of the datasets, which is great. Furthermore, the better the model we have, the smaller the gap between private and non-private accuracy. And this is especially encouraging because it means that as models keep improving month after month, year after year, we can expect the private and non-private gaps to continue decreasing. In fact, as you'll notice, there's a point down there on the bottom right-hand corner where the gap is actually 0. And that's actually our result for CIFAR 10, where we obtain the same performance of 99.00 accuracy for private and non-private training while accounting for the privacy cost of hyperparameter tuning. So as these models continue to improve, we might expect to see that other benchmarks like Fashion MNIST or maybe even CIFAR 100 could similarly be solved, so to speak. And finally, we're going to take a look at linear scaling for the full fine-tuning setting where we're updating the entire model. Now, we do have some theoretical guarantees, which we won't get into in this talk, but these theoretical guarantees only hold for linear models. Does linear scaling continue to hold when we train a deep model? It turns out that the answer is yes. Even when we train the full GPT-2 model, which has over 100 million parameters, linear scaling holds on the next word prediction task of persona chat, and in fact outperforms some competitive prior work. So just to quickly leave you on a summary slide, in case there are any questions, we found that the hyperparameter search for DP fine-tuning costs a lot of privacy, and we came up with a linear scaling rule that allows us to account for this privacy cost by using a small budget to find the best value of the hyperparameters, and then scaling up those hyperparameters as the privacy budget increases. We incorporated this into our overall recipe for private fine-tuning that is an optimized version of DP-SGD. This optimized recipe does full batch gradient descent with momentum from a zero initialization and takes a final free step without adding noise. We observed that across a wide range of tasks, private fine-tuning can achieve incredible performance, including lossless privacy on CIFAR 10, while including the cost of hyperparameter search. for both linear probing and full fine-tuning of deep transformer models. In future work, we might explore extensions of the linear scaling rule to training from scratch, but I'll pause here for any questions before we move on to the next part of it.
Hello, Xinyu. Thank you for the talk. Very interesting. I know that I noticed that you are tuning that learning rate times epochs, and then you mentioned something about the clip. You set that to 1, but the clip for DP-SGD is particularly sensitive, right? Like you can get very different results depending on how you clip. How do you decide how to clip? Maybe I arrived late.
Yeah, so I think in the specific algorithm that we are using, we're actually dividing by the amount that we clip by. So typically when you use different clipping thresholds, the clipping threshold has a factor of the clipping that turns into the learning rate. But by dividing by the clipping, and this update rule is used in D et al., the well-cited work from DeepMind from 2022, that clipping factor actually sort of vanishes out. So that's why we're able to use a unit clipping norm and not really have it affect. That is to say, the choice of the clipping norm doesn't really affect other stuff because it doesn't turn into the learning rate. We also do have an ablation on the value of the clipping norm, if you'd like to see that.
Thanks. I can take a look. Yeah, I guess I arrived to like the second half of it. Thank you for taking the time to answer that question.
No problem. Okay. If there are no other questions, I'm going to turn it over to Xinyu for the second part of the talk.
Okay. Thanks, Ashwinee. So Ashwinee just talked about the linear scaling rule for DP-SGD when model pre-trained on large public data is available, and we saw the compelling results on both vision tasks and also natural language tasks. In the next part, I will talk about the second case with public data, where only the limited public data is available, and we propose DOPE-SGD to effectively leverage public data to improve DP-SGD beyond pre-training. Given the limited public data, we can pre-train a model on public data to initialize a better model. And this is also how most previous work leverage public data to improve the utility for DP-SGD. We call this setting as DP-SGD warm. As in this assumption, we only have limited public data, the utility gain by DP-SGD warm is also limited. For example, we consider an experimental setup for CFI10, assuming 2,000 images as public, and DP-SGD can achieve accuracy of 68.1%. This is a 3% accuracy increase compared to the DP-SGD without public data. However, 68% is still far away from the non-private model, which can easily achieve more than 95% accuracy. Given this situation, we are curious about this research question. Could we effectively leverage limited public data to improve DP-SGD for privacy-preserving machine learning beyond pre-training? As we can see here, there are 4 steps in the learning procedure: pre-training on public data, preparing a dataset, privately train a machine learning model by DP-SGD, and finally, deploy the trained model. As the pre-training on public data is just a first step, and by carefully investigating how to leverage public data in these 4 steps, our answer to this question is yes, and we propose DOPE-SGD. Specifically for this experimental setup, our DOPE-SGD can achieve a classification accuracy to 75.1%. This is a 7% accuracy increase compared to the DP-SGD1 baseline. In the following slides, I will show you how we achieve these improvements step by step. One comment here is that as we are assuming 2,000 images public, we are comparing between the DP-SGD1 as a baseline to improve instead of DP-SGD without public data for a fair comparison. Let's get started with the first step, pre-training on public data. The work by D et al. Has shown that data augmentation of private data in DP-SGD can improve utility. Given the limited public data, could we also apply data augmentation technique on public data to further enhance the quality of public data? The answer is yes. To be most concrete, we can use generative models. Why generative models help? Well, If we train a generative model on public data, we can query public data from this generative model without incurring additional privacy costs. For example, we can use diffusion models for image datasets. One comment here is that this technique is not limited to diffusion models. We can use different generative models for different data domain and tasks. We call this setting as warm aug, and by applying this technique, we can achieve classification accuracy to 72%. Next, we proceed to the second step, preparing a dataset. As we now have a public dataset and private dataset, instead of just apply DP-SGD on private dataset, we can combine this dataset together to get a mixed training data. The advantage here is that we can have a larger training set. Therefore, with the same batch size setting as private data alone, this can decrease the sampling rate. Therefore, with the same training steps, we can add less noise for the same privacy budget. We call this setting as extended, and by applying this, we can achieve classification accuracy to 73.7%. Next, I will talk about how we leverage public data in the DP-SGD step, where we use a technique called origin estimation. First, I want to give a brief review of the DP-SGD step. As we know, it will clip the gradients and add noise. So here is a brief animation. The dashed blue lines is the non-private gradients, and we have a clipping bound. And we apply the clipping bound to get the clip gradients. This green circle is a random noise range. We randomly generate a noise and add it to the clip gradients. This solid light blue lines is the final privatized gradient. The clipping the sample gradient would result in a utility drop. The good thing of public data is that we can leverage public data to help mitigate this issue. The design intuition of origin estimation here is that instead of clipping the gradients around the zero origin, we will clip the gradients around the estimation of the gradient to reduce the effect of clipping and noise in the privatized gradients. And this estimation of gradients can be from the gradients of public data. So here, I just want to show you a brief animation of this how origin estimation works. Again, this is a non-private gradients, and this purple line is the gradients from the public data. We have this clipping bound to get the clip gradients, and this is a noise range, or we add noise to the clip gradients, and we finally get the privatized gradients. As shown by this animation, here we can see that the privatized gradients given by origin estimation could have a larger norm and also a relative higher signal to noise ratio compared to the original DP-SGD step. Therefore, with the same privacy parameters, the origin estimation method can achieve better utility. Here we also provide a justification of this intuition for why origin estimation helps. This is because the origin estimation can contain more information of the non-private gradients. Here is an example experimental result on CFA10, where we do the inner dot product of privatized gradients and non-private gradients. A blue line is the inner dot product from the origin estimation in DOPE-SGD, and the red is the one with DP-SGD. As the DOPE-SGD has a higher inner dot product, therefore, the privatized gradients provided by DOPE-SGD is more correlated with the non-private gradients. By applying this origin estimation, we could achieve another 1% classification accuracy increase. After we train the model, we come to the stage to deploy the trained model. We know that in the non-private setting, the number of multiple models is used to boost the utility. So how about in private setting? The good thing is that based on the post-processing technique property of differential privacy, we can leverage the intermediate checkpoints without additional privacy costs. We can do model ensemble among multiple model checkpoints to further boost the utility. The work by Di et al. Has investigated the method of exponential momentum average to improve utility, and we also investigate majority voting and averaging predictions of the last N models. By applying this number technique, we can achieve classification accuracy 75.1% in this experimental setup at epsilon equal to 2, assuming 2,000 images as public. Now I have introduced all techniques we considered about how to leverage public data in all these 4 steps. And here I just want to show you some more results at the evaluation at more privacy levels, ranging from epsilon equal to 1 to 6. And we can see here at each evaluated epsilon, our DOPE-SGD can have an improvement compared to the DP-SGD 1 baseline. So a brief summary of DOPE-SGD is that instead of just pre-training on public data to initialize a better model, we can incorporate public data in each step of this learning procedure to have a utility increase. And for example, here we consider how to augment public data and apply the origin estimation. And in this experimental setup, we can have a 7% increase compared to the DP-SGD 1 baseline. Now I want to have a summary of our presentation today. In this talk, we talk about how to leverage public data to improve utility for DP-SGD, and we talk about linear scaling and DOPE-SGD. Linear scaling is considered for setting where models pre-trained on large public data is available, and we propose new algorithms for fine-tuning with DP-SGD by using linear scaling rule with few hyperparameter search trial and achieving companion results both on computer vision tasks and natural language tasks. And DOPE-SGD is for setting where only limited public data is available. And the key point we want to make here is that we want to effectively leverage limited public data to improve DP-SGD beyond pre-training. For example, the data augmentation and also the origin estimation in a DOPE-SGD. We have seen in this talk that public data help a lot in DP-SGD. Some follow-up questions can be, could we relax the public data assumption? For example, just as Ashwinee mentioned, for linear scaling, would the linear scaling rule also hold for the model training from scratch by DP-SGD? And secondly, for DOPE-SGD, could we also provide a privacy protection for the public data we use? For example, instead of training a generative model directly on public data without privacy costs, could we also provide privacy guarantee for the generated images for origin estimation? Now I want to conclude our talk today, so feel free to try our code on GitHub for the linear scaling, and the code for DOPE-SGD is also coming. Thanks, and we're happy to take any more questions. Okay.
Thank you. I'll turn off the recording for questions.